This is not. Come on, silly thing. Really no suggestions. There we go. Alrighty, let's get started for today. Hi, little Rooney. Alrighty, so we're gonna talk. Yes, happy St. Patrick's Day. Oh no, and I'm wearing a black shirt instead of a green one. Ah, you know what? Let's see. I have some green sweatpants I'll wear later, perhaps. That seems appropriate. So we'll do that. Okay, so we'll talk about some entropy fun stuff. We're going to take another closer look at what entropy is. And I really like the book's example for this. I think it illustrates it in a pretty clear way. So we'll just kind of reiterate that. So if we think about entropy as... So we kind of talked about yesterday having like the, container that had a, barrier in the middle. I'm just going to copy this one because we're going to need it a couple of times. Where you have, we'll say, two gas particles, because of course we can just have two, right? Very easy. But it's an example, so we'll be okay. Where we have them both on one side of this flask, and there's a barrier in the middle preventing them from moving. And so, actually, let me delete that one. Let's do it down here. If we open that flask, we have a couple of options as to what's going to happen. As in if we open that middle part. We have the option where we have... Here, I'll just draw them. Where the green one can be on either side. Oops. These are kind of the four options we would get, right? Just if we were to... relax, creature. If we were to kind of take a look at a given moment in time, these are the four options we would have, right? We could have the green one on the left, the blue one on the right, both of them on the left, both of them on the right, or one on, opposite sides of the first one. So with that in mind, we can see that this model has four what we call microstates. So again, we're kind of just looking at a very simple case where we have two molecules. And those four microstates are both left, both right, and then we have blue left, green right, and then the opposite of that. Right, so we have four microstates here. And it turns out, because we have two particles, we see that the number of states, microstates rather, is 1/2 to the second power, because we have two options, left and right, and we have two particles. And so we end up with a fourth probability that we'll have one of these particular states. So if we wanted to see how often we would have both of them on the left, that would be about 25% of the time. Or if we were to look at the bottom right one, that would be another 25% of the time. And so we can see here that this is just a probability measurement, rather. So this isn't. This is going to be the number of microstates on the bottom. We have four different states happening here. And so this is just with two molecules or two particles. And if we expand this to a mole instead, it's a really, really small number, right? 1 over 1 kajillion. Whatever that happens to be, fine. 1 to the... I don't even know. Something very, very small, right? So we can see here that if we were to kind of do that, the probability that 1 mole of gas is located on only one side of the flask is essentially 0. And we know in real life, if we were to open that, the gas would spontaneously expand to fill both sides. And just as an equilibrium, they would be just shifting around, all the time. But the likelihood that all of them will migrate to one side is really 0, right? It's 1 over this crazily large number. So it's just not going to happen, right? It's essentially 0. And so we can see that this is a kind of macro explanation of entropy. So entropy all talks about kind of disorder, right? The likelihood of them being organized and orderly and on one side is 0, because entropy will always favor having more options. And we can see that a scientist named Boltzmann studied a lot of this stuff. We have the Boltzmann distributions that we talked about with temperature back in, what was it, the gases, I guess we talked about temperature. And we saw that at different temperatures, you'd have different proportions of molecules with different kinetic energy. Those are all snapshots of microstates. So if we take a look at, for example, we had the temperature and then the proportion of molecules, or rather, this is kinetic energy, not temperature. We would see that, okay, we had something like this, right? Where we would have, well, eventually this would, reach the bottom, but we saw it was a distribution somewhat like this. And we can see that for this, potentially we have, for 1 mole, we have 10 to the 23 microstates. So each of these individual, points in here is a microstate. Or rather, each kind of line is a microstate, and it might be populated by a whole bunch of different molecules. So this microstate has it at, this particular kinetic energy for this given temperature. And maybe there's, this many molecules that are occupying that microstate. So you have a seemingly infinite number of microstates, all of these lines here. We know if we integrate, we're just adding all these lines up. All those lines represent microstates. So we have tons of them. And we see we can relate entropy to microstates using a constant. This is Boltzmann's constant. Which I do not remember. Let's see what it is. Okay. 1.38 times 10 to the negative 23? Yeah. Joules per Kelvin. Notice that this, of course, will take the same unit as entropy, because if you do a natural log of something, there will be no units. So, of course, it should be the same unit as entropy. And W is the number of microstates. So again, microstates are kind of snapshots of all the given kind of conditions of a particular molecule that it could have. So it's kind of conceptual, right? Snapshots of conditions that a given particle could have. And that can be all sorts of things. That could be position, that could be vibrational state, rotational state, just kind of how quickly it's moving. All of these things are kind of conditions. And so we see here that, of course, Boltzmann's constant is very small, right? 10 to the negative 23. But we see entropy as values typically in the joules per Kelvin range. So we can see we're often dealing with somewhere along the line of having the natural log of W be 10 to the 23 or so. Thereabouts. 10 to the 24, 10 to the 22, thereabouts. So that's a very, very large number in order to get a natural log that big. Yay, new email, hooray. And so this is not something that we're going to deal with. Of course, it's unfeasible, right? To think of, okay, I have this sample of whatever, and it has 10 to the 23 possible things it could do. Let's look at all of them. No, we're not going to worry about that. We're not even going to really use this equation necessarily. It's something that's more theoretical for us. But it does help to explain the third law of thermodynamics, which is the last one that we're going to talk about in this chapter. So with that being said, we can see that the entropy is not necessarily is all about like what molecules could do. It's all about possibilities. And the more possibilities you have, that's more entropy. And if we think about it, we kind of have this, basic idea that the entropy is just chaos or disorder. But it would be more accurate to say that it's all about just how many possibilities you have. And that is somewhat like randomness, right? We're going to see that there's going to be a lot of things we can do to increase the entropy of a system, to kind of just give it more possibilities. For example, we know that if we increase the temperature, we shift the graph over, right? That will give us more microstates. We end up moving our graph over, but we still have that kind of little bit at the start. So we just have more microstates at higher temperature. And so we're going to see that if we increase the temperature, increase the volume, or increase the moles of a particular substance, all of these will increase the entropy because you have more possibilities, right? The more space you have, the more volume that is, the more locations a particle could be in. That's more possibility. The higher your temperature is, the greater your distribution of kinetic energy is. And the greater moles you have, of course, then you would just have the more possibility for, two things to be close together or far apart, or, being in a triangle formation. There's all of these possibilities that we look at. And so all of these factors will contribute to having more entropy. And so it's a very, as you can imagine, complex topic to say it, as most basically as possible. People spend their entire, graduate or professional careers studying entropy because there's so much you can do with it. It's such an important concept. And so if we want to kind of think about all of this stuff, we can kind of qualitatively analyze how entropy will change based on these factors. And we kind of touched on this yesterday. But since we have this idea of more possibilities being more entropy, we can look at the states of matter again and see why gases will have more entropy than the others. So, solid, here we go. If we look at a solid, we know that solids don't move around each other, right? They're fixed in place, but they do have vibrational states. They are moving, they're oscillating back and forth very slightly, but those are different possibilities. So as they do that, they are still creating entropy as they vibrate in place. Liquids not only can vibrate, but can also rotate. So they'll have different vibrational states and rotational states. So this liquid molecule, let's say, it's half of it is blue. If we look at it at a given time, maybe it's now over here where it has the blue part up there. And it can also move in place. So it can rotate and it can vibrate. And so it has even more entropical possibilities. So liquids are definitely more chaotic, more disordered, have more entropy than solids do. And if we look at gases, they can not only vibrate and rotate, but they can also translate. And that means they can move, left, right, up, down, back and forth, actually move over distance. So that would be more like changing location, kind of. So technically liquids can do this as well, but gases are much, much more likely to translate than liquids are. So as you can imagine, we can now have this particle moving all the way over here while also spinning around, while also vibrating. And so it can do all of these sorts of things. So it can vibrate, it can rotate, and it can translate. It can move. So we can see here we have quite a few more possibilities, exponentially more for a gas. And so we see again that gases are going to be much more entropic, as it were, than liquids or solids will be. And so we also saw that if we were to look at, if you want to kind of look at these in terms of like actual molecules, we can take a look at a water molecule. Here it is. If it's going to vibrate, that might look something like this, where it will have shortened the bond between the oxygen and hydrogen, and maybe it lengthened the other one. Bonds are always kind of vibrating like this. They'll move back and forth. What we call bond length is really the average bond length, but bonds are continuously shortening and elonging. Elonging? Yeah, I think that's a word. Anyways, they're getting shorter and longer all the time, and that's what vibration is. So these bonds are moving closer and farther away from the oxygen atom. And so that's happening all the time. So that's a different state. If we think about it rotating, it's going to be kind of swirling in place there. Not something that can happen in a solid. This is rotating. He's so cute when he plays with this toy. And then translating, that's the easiest one, right? It's at point A. Here is point B. And now it is at point B. Hooray. So it can move, right? And all of these can happen at once. So it can translate and rotate at the same time, or translate and vibrate at the same time. And there's all sorts of other vibrations that can happen. This is just kind of, moving in this direction. But bonds can also vibrate like... we talk about this a lot more in OChem, but we can go from this to this. Okay, that's out of... No. We can also have them kind of move very close together. We could have them move very far apart, angle-wise. Again, we're looking at average bond angles when we talk about bond angles, but those can bend back and forth as well. That's another vibrational mode. You also have ones where they're, if we're thinking about yoga is a great way to explain vibrational modes. Can we see me? Yes. So, let's make myself a little bit shorter here. Okay. So, I'm a water molecule. I can move my bonds like this. That's a vibrational mode. We're doing our yoga exercises. I could move my bonds like this. I can twist around. That's rotation, right? Let's see. What else can I do? I can move my bonds this way as well, as well as that way. So I have all my exercises here that I can do, and so there's all these different vibrational modes that your molecules can do. And we see it gets more complicated. If we have more atoms, that's more modes as well, more vibrational modes. So, it's kind of easy for us to just look at a 3-atom system here. But if you have 10 atoms, all of those can be, doing all their fun little things. Potentially. So when they gain energy, it depends. For it to actually break, we're going to see that these actually will obey Hooke's law to an extent, where the force that they're going to experience is related to a constant times their displacement. For the rest of you non-Kevin people, ignore this. There is, so normally you think of Hooke's law like this, right? Where you have energy and then displacement. So for a spring, the more you stretch the spring, the higher the energy goes in either direction. If you compress it, it wants to re-expand. If you expand it, it wants to contract, all to get to that kind of zero energy. However, what we see is that eventually, yes, we see what's called anharmonicity here, where eventually, if you stretch it long enough, it will indeed break off. Yes, that is a potential with a vibrational mode that you can break it off. But chances are it's just going to reattach, just because many of the CH bonds that we deal with in organic chemistry, they have pKa's of about 50 or so. So you can imagine the pKb would be negative 36 then. So extremely, extremely strong a tendency to reattach itself. So technically, yes, you're going to see that this is a point of more reactivity for sure. If you have something else to take it away or to replace it, yeah, that's a point of reactivity for sure. And so this is happening all the time. They're constantly vibrating. So, okay, let's erase all this so nobody else will see it or get confused. Actually, it's kx squared, isn't it, now that I think about it? Oh, of course, because it's a parabola. So, anyways. Point is, that aside, we do have more vibrational modes here the more atoms we have. And we're going to see that we can talk about standard entropy states for a particular molecule and how they will kind of change. But before that, do we have any other questions on this? So just to kind of reiterate, we saw that we can kind of qualitatively, we said this yesterday, but we'll say it again. Delta S is positive when we go from solid to liquid or solid to gas. If we go from liquid to, I want to say liquid to gas here, or from solid to gas. Yeah, let's actually just keep the gas ones. And then here we'll have solids to liquids or solids to some sort of dissolved state. And then the last one we talked about was fewer gas molecules to more gas molecules. So if we think about, we had that thing way back here. Let's copy this whole thing to see that last bit. Okay. If we look at this and we say, okay, instead of having two molecules, let's throw a third one in. We're going to have now 8 possible states where we can put that purple molecule in any of these, right? And so we can see we have more states with more molecules. And if you want to think about that, you know, for example, if we had, we have absolutely our favorite reaction of all time. We saw how we could mess with the equilibrium with this with changing the pressure, right? How we could influence it moving to the side of more or fewer molecules. Entropy will favor this one. So this process right here, delta S is negative for this process, right? We can see that because we're forming fewer molecules as a result. So the more gas molecules you have, the better your entropy is. So the change in entropy for this reaction, we're going from 4 gas molecules to 2, that will be decreasing the entropy because you're removing possibilities of what they could do. So, lot to think about here. But thankfully, so this we talked about yesterday. We did go over these, but we'll do it again. If we throw that in here, you know, now we have the purple one being here or here. Actually, it can be in all 4 of those. Then we could duplicate them again and have the purple one now on the right. And those would be the other states. So the more molecules we have, the more states we have, the more entropy we have. Hooray! Alrighty. How are we feeling before we talk about our last little bit of thermodynamics? Alrighty, here we go. The third law of thermodynamics. And this one is going to be that the delta S, actually not even delta, it's just S. Just S. For a perfect crystal, I don't know how to spell crystal, at 0 Kelvin equals 0. So remember, at 0 Kelvin, we do not have vibrations anymore. Right, that's how we define absolute zero, where there is so little energy that molecules can no longer even vibrate. So they can no longer stretch their bonds or just buzz around in place or whatever. That can't happen at 0 Kelvin. And so if we think about this, that means that W is 1. We only have one state it can be in. It can't vibrate, so there's no other states. And so the natural log of 1 is 0, right? So your entropy becomes 0 for that. And so this is just kind of, again, theoretical. We've never really reached absolute 0, but this gives us a kind of base point. If we can have a 0 for entropy, we'll be able to compare other things to this and be able to assign them quantitative values. So again, this isn't really necessarily important directly because we don't really have perfect crystals and we don't have 0 Kelvin, but with that, we can use this as a baseline for having, if we have one state, we have 0 entropy, and from that we can kind of mathematically calculate other entropy states for other things. So it's just kind of standardizing the 0. And then from that, we can see that we're going to get entropies for various things. Actually, let me go ahead and get a table for you guys. We'll have yet another table, our favorites. Standard entropy table. Here we go. Is this a good table? Yes. So here we go to the YouTube, not YouTube, what is this called? We're going to see that all of these fun things are going to have various entropy states. And notice we have all sorts of, these are just kind of two columns, but they're not different. Like, it's just condensed. So this is really just one chart, but they put them, in this case, all together. Notice that all of these values have two things in common. If you remember delta H for something like helium or bromine or iodine or lead, what was delta H formation for these things? For graphite, for example, or oxygen. Delta H was 0, right? But we see that 0 for entropy is defined as that, yeah, right. So entropy is defined as 0 for that perfect crystal at 0 Kelvin, which is not possible, right? And so everything will in fact have a non-zero entropy value. And so these have been calculated, of course, experimentally for us. By actually calculating equilibrium constants, you can figure out the molar entropies doing a lot of back calculations. So we can see here the point is non-zero. And notice we have these kind of monoatomic species, all, roughly below 100 for the monoatomic ones, right? We split into diatomic. Notice what happens here. Just trend-wise, we go to triatomic or polyatomic. Notice they get bigger and bigger and bigger as we go through. And notice what happens as we go from solids, say around 50 or so, to liquids, to gases, typically go up, right? So if we look at a monoatomic solid, let's say sodium, 50, monoatomic liquid, 75, monoatomic gas, 126. Yes, exactly. So, and then, yeah, so Kevin's absolutely right for the, as you go from monoatomic to diatomic to triatomic to polyatomic, of course you get bigger because you have all these different vibrational states that you can have within your molecules. So we're going to see here, those are the trends that we're going to see with entropy values. So, hold on, let me cancel that. Okay. So that being said, we're going to see that we have what are called standard entropy values. Those are going to be at either 1 atmosphere or 1 molar concentration, if you're looking at a gas or a solution, or they're just going to be at 1 atmosphere pressure for solid liquids gases, and for this is for solutions. So these things are going to be it's never zero, right? Because we saw that third law of thermodynamics will define zero for us. So for our real things, we're not going to have zeros. We're going to see that this increases with number of atoms. We're going to see it also increases with molecular mass or molecular weight, molar mass. We see this also goes up with the state of matter, where solids, these are just trends, right? So they're not absolutes, but typically the more atoms you have, the larger your molar mass is, and your state of matter will all affect, generally speaking, your standard entropy value. And guess what we can do with these? We're going to see that we can do some calculations. Right? So just like we did with delta H and delta HF values, we can calculate the delta S for a reaction by looking at, just like before, the products minus reactants. Productus. Of course, multiplied by their coefficients. So just like before, like we did with entropy and bond enthalpy and all this sorts of stuff, we're looking at the chemical equation. We can figure out the delta S for the reaction by looking at the standard entropy values for the products minus those for the reactants. So let's go ahead and do it. Here's our favorite reaction. So H2 plus 3H2 plus N2, 2NH3. We predict that it will be negative, right? Because we have fewer gas molecules in the products. But let's go ahead and actually calculate it. So delta S for this is going to equal 2 times the S for ammonia minus 3 times the S for hydrogen plus 1 times the S for nitrogen. Let's go ahead and go back to that table and let's get those values. And so we can see here we have, let's see, we're looking at diatomic gases. So nitrogen is 191.6. These often take the units joules per mole Kelvin, just like we had similarly joules per mole for, or kilojoules per mole for the delta H's. This time we do have the Kelvin factor in there. What were we looking up? Hydrogen also? Oh, it's up here. 130.7. And then ammonia is going to be here in our polyatomic gases. It's 192.5. And so let's see if Kevin can calculate this for us. Thankfully, I have the value here. Joules per Kelvin. Hooray! And Of course, we did expect this to be negative because we are making fewer molecules. And indeed, what we do calculate is that it is about negative 200. So indeed, we have an entropically unfavorable reaction. Good enough. Close enough. Here, we'll make you happy. There. So there we have it. Let's do another one. Let's do electrolysis. So this is a process by which we apply electricity to get this reaction to happen. If we're looking at this, what are we expecting delta S to be, positive or negative? Yeah, it should definitely be positive, right? We have a number of reasons for that. Not only do we have liquid going to gas, but we have 0 gas molecules to 3 gas molecules per reaction, right? So we have a number of things here telling us this should definitely be positive. So the delta S for this reaction is going to be 2 times the S for hydrogen plus the S for oxygen. Remember, these are not 0, as they would be with delta H, but not for this, right? And so we would have to subtract 2 times the S for liquid water. Your state of matter does matter, as just like with delta H, right? We would need to know the state of matter. So we're going to need to remember that this is the liquid water. So we can go ahead and do this. Let's find them. We have hydrogen. We have actually liquid water here, 69.9. Let's just copy that one. Hydrogen gas was 130.7. I'll find a good table to put in Discord for you guys, because this table doesn't really have very much, believe it or not. This is a pretty small table. The one in our book actually is really, really thorough. It has delta S, delta H, and delta G for all of these various substances, including various compounds. Okay, so we have our values here, and Kevin will provide us with the answer, but we can already see this is going to be a very positive number. We're going to have something like 460 minus 130, so this is going to be a pretty big number, 300 something, right? So, but let's see what Kevin gets, because I'm too lazy to calculate it myself. Awesome, yeah, 326.7. So a strongly entropically favorable reaction. And so the reason this doesn't happen by itself, of course, is delta H, right? We're going to see that this is going to be an extremely endothermic process because hydrogen and oxygen would have 0 for their delta H's, right? And so we're going to see that that's what's going to prevent this from happening spontaneously. We have to actually apply a pretty strong electric current to get this to go. All right. Questions on that? Alrighty. So with that in mind, if we go ahead and compare some of these things, let's go ahead and let's do the delta H reaction for the ammonia. So let's pull up our other table of fun things here. We're going to have to actually, I think, go back to 111. Where is the... Yeah, this one. Okay. So, oh, in fact, this table actually does have delta S values, so we can just use this one. So that's good. So if we're looking at delta H for these, remember it's the same thing. We use the products minus the reactants. So we're going to look all these things up. We have ammonia here. We're looking at ammonia gas. So the delta H for that. Is going to be 2 times ammonia's, which is negative 80.3, minus ammonia and hydrogen, right, which are, hopefully we remember for ammonia and hydrogen, they should be 0 because those are the standard states, right? Oh, I copied the wrong one. I copied the aqueous ammonia, 46.2. So if we do that, we get what? Negative 92.4 kilojoules per mole. Please confirm, Kevin. Okay, good. If we kind of compare that, if you remember how we could look at the delta S for the surroundings, we saw that we could use delta H over the temperature, right? So if this is happening at room temperature, which is what these standard conditions would tell us, we're going to see that that would be can I get this answer, Kevin, in joules per Kelvin, please? So we have kilojoules on the top. We have Kelvin on the bottom. I don't want to calculate it. No, actually, we typically will use the positive value because... Or will we use the negative one? Oh, no. This should be because the surroundings are going to be absorbing the heat. The reaction is giving off the heat, so this should be positive, right? It should be the opposite one. Yeah, so... are you sure? I would think that it would be one more thing, because we have 92,000 over 300. So it should be 300 then. Or at least 90,000 over 300 is 300. So double check that, please. Remember that this is delta H for the surroundings, which would be opposite of delta H for reaction, so it's going to be positive here. Cool, awesome. Okay, so with that in mind, let's just double check our... to see if this reaction will be spontaneous or not. Remember that's delta S for the system, plus delta S for the surroundings. We calculated delta S for the reaction to be negative 200 or so. And we saw that the delta S for the surroundings will be 310. If we could have this answer here, I believe it is 112. Which tells us, what does this tell us? This tells us it's a spontaneous reaction, right? Remember, if... Okay, close enough. A spontaneous reaction will always increase the entropy of the universe, right? That's the second law of thermodynamics. Will tell us this is spontaneous or not. And so this is how we can use these delta or standard entropies to figure out what if a reaction is spontaneous or not. But there is an easier way. Rather than having to do all this like delta H, dealing with the temperature and then dealing with the calculating the entropy like this. And we talked about it yesterday. So some guy in the 1900s came up with this idea of free energy. And that now will expand our... we saw we had that boulder going down the mountain. But now we're expanding that into the boulder rolling into a valley. So we're going to see that as that boulder rolls, it might roll up a little bit, and then it's going to roll back down and back down and back down and back down, back down, at which point we will reach equilibrium. And we're going to see that this is going to be the same thing for a chemical reaction. We're going to see that if we're just kind of looking at reaction progress, for example, we're going to see that the reaction will be spontaneous from either side of the equilibrium. And that's how equilibrium works, right? We know that it's going to, you're eventually going to produce all these products, and then some of those products are going to break back down again, and you're going to make them back into products and break them down again, and eventually you'll reach that kind of zero net change state where everything is happy. And so that happens spontaneously, right? You have your reaction happening in the forward direction. Eventually, too many products are made, and you have the spontaneous reaction happening in the reverse reaction. And eventually you reach that equilibrium point. And so we see that if we were to actually plot this as a graph, we're going to see that this is what's called free energy on this side. And this is going to kind of be your reaction progress. Or it can be your kind of Q. We can think about it in terms of Q. So remember, as Q goes above K, that's this point, we end up going backwards. If Q is less than K, we end up going forwards. We kind of saw that sort of thing happening before, right? And we can relate what's called free energy, which is G, which is for a particular substance, its enthalpy minus its entropy times the temperature. Or what's more often used is we look at the change in free energy. One of the dogs is barking outside. I have to get him, but let's let him bark for 3 more minutes. We'll be okay. So this is that reaction that I had introduced yesterday, where we can see we have the free energy, we have the enthalpy term, and then the entropy term, and then of course the temperature in Kelvin. So, oh gosh, what units does delta G take? Oh my goodness gracious. What do we think the units are going to be here? So if we think, we typically will have joules per mole minus Kelvin times joules per mole Kelvin. So delta G will also take units of joules per mole. So not very exciting. Or you can just look at the units of delta H. You don't even need to worry about this Kelvin stuff. So you'll see that it will follow those units. You can use kilojoules per mole, of course, as well. Doesn't really matter. You can use either one here. So with that in mind, we can use these sorts of things. We see that for any spontaneous process, if delta G is less than 0, a reaction will be spontaneous in the forward direction. If it's 0, that means the reaction is at equilibrium. And if it's greater than 0, it will be spontaneous in the reverse reaction. So it'll happen backwards. And this will be, again, for any equilibrium reaction. So it's kind of just depending on where you are, right? So we're going to see that we can relate delta G to Q, because remember, Q shows us where we are in our progress towards equilibrium. And we're going to see that we can relate delta G to Q. We'll also be able to relate it to equilibrium constant K, either Kc or Kp, depending on what we're looking at. But that we're going to have to do next week, I think, because I don't want to go too far out of here. If we kind of just look at delta G from this reaction itself, I kind of did this chart yesterday, but we saw that some reactions, here we can do this. If we have delta H, delta S, what will happen with delta G? So if we have delta H being positive, that means endothermic, and we have a positive entropy, we see that this is one that is going to be favored by high temperature, right? Because we want delta G to be negative, so we want that S term to be bigger. So we're going to see that high temperature would mean this is spontaneous in the forward direction. We see that if it's the opposite, if we have an endothermic reaction that is entropically unfavorable, it's never going to happen in that particular in that direction. If we have an exothermic reaction, it is always spontaneous if delta S is positive. And for the last one, we're going to see that the other one will be spontaneous at low temperature. And these will all be the opposite for the reverse reaction, right? So we'll see. This is delta G for the forward reaction. So we're going to see that these are going to be kind of the guidelines, as it were, for what we're going to do with this sort of thing. So we're out of time for today. We will continue on talking about this stuff, doing some actual calculations with it, using these standard values for enthalpy, entropy, and free energy. And we'll work on that on Monday. So we'll continue on with this stuff. And I guess we'll see you then. So honors people, I'll see you tomorrow. I think we're far enough along that I can give you questions on this. So we'll have that. Alrighty. If there's nothing else, see you later.